All right, so here we have cases where our fractions have denominators that are different. All right, so in the previous video, we were doing these sorts of problems where all the denominators were the same. All right, now we're gonna take it up a notch and all of these denominators are gonna be different. All right, so now we need to figure out how to solve x in a scenario where we have different denominators. All right, so long story short is we need to make common denominators so we can really be able to combine these fractions. You can't combine fractions if they have unlike denominators. So let's make sure that these denominators are ultimately the same. Okay, so there's two techniques that we can use to figure out these kinds of problems, these two problems that we have here. We're going to start doing this problem, and then the technique that we use with this problem, we're going to apply to this more complex problem, okay? So you can sort of disregard this problem right here for the second. We're just going to be working on this one right here. Okay, so since we have 5 and 10 and 15 in the denominator, these are all clearly different, so we're going to have to find a common denominator, okay? The way that I like to think of finding a common denominator is I look at the largest denominator, in this case it's 15, and I see if the other denominators can go into 15, right? Meaning are 5 and 10 factors of 15. 5 is a factor of 15, but 10 isn't, all right? So the easiest way that I come up with a common multiple that all of these go into is I will take the largest denominator and I will increase it by a factor of 2, a factor of 3, until I see that all of these are can be divided in a whole number into whatever our ultimate common denominator is going to be. So, okay, so none of these, so 5 goes into 15, but 10 doesn't. So let's try 30. Let's increase this by a factor of 2. Let's try 30. Okay, does 5 go into 30? Yes. Does 10 go into 30? Yes. And clearly 15 goes into 30 because I doubled 15 to get 30 in the first place. So that means that I need to, so this is the least common denominators, all right? Least common denominator here is 30. Now, it doesn't mean that you have to use the least common denominators to do this kind of problem, but isn't it easier that if you're going to have to work with larger numbers, why don't you work with the first number that all of these work with, okay? These all might be 15, 10, and 5 might all be factors of 90, but isn't it 90 would be a common factor of all of these. I'm sorry, a common denominator of all of these. But wouldn't it be easier to work with 30s instead of 90s? So that's why we're doing the least common denominator, okay? All right. So in that case, if I want 3/5, and we're going to have to look at each one of these fractions individually. If I want to represent 3/5 with a denominator of 30, okay, how did I get from 5 to 30? I need to multiply it by 6, all right? So that means the numerator needs to be multiplied by 6. So 3 times 6 is 18, meaning 3/5 and 18/30 are equivalent fractions, all right? They're equivalent fractions. We can make a proportion out of it. So I haven't changed the quantity any, I've just translated what those quantities look like. That's okay. Like this could be English and this Spanish, but they both mean the same thing. You know, this could be the word table in English, and this would be the Spanish word for table, mesa, all right? But do you see that they're translations, but they mean the same thing? So that's why these are not changing the problem at all. Same thing for 10. 10 goes into 33 times, all right? So yes, I understand there's an x here. Variables are fine, but we know that there's going to, whatever this variable is, ultimately, we know that we need 3 times that variable, 3 times that value, so that this fraction and this fraction are equivalents, okay? And then Finally, we multiplied 15 times 2 to get to 30, so we need to multiply its numerator by 2 to keep the same equivalent fraction. So 2 times 6 is 12. All right. Now do you see that we have common denominators here? So now that we have common denominators, we can then work with these fractions. All right. So 18 30ths minus 3x 30ths. All right, since the denominators are the same, we keep the denominator and we do whatever the operation here is. So if this was an addition, we would add 18 and 3x. Since this is a subtraction sign, we'll subtract 18 minus 3x. Great. And then we leave 12 over 30. Okay, so there we are. And now, to get rid of our denominators, why don't we multiply, oh, by the way, just to be safe, let's put this in parentheses. Let's multiply both sides by 30 over 1. Do you see if we and what we do to one side, we have to do to the other to keep it balanced. Do you see if I multiply both sides by 30 over 1, the 30s cancel out. I just get 1s, okay? And so those cancel out to 1s, so we don't need that anymore. All right. So what we have is 18 minus 3x equals 12. All right? Now, let's use our properties of equality and inverse operations. So we want to isolate x. We want to get x all by itself. So let's start by clearing away that 18 there. Subtract 18 from both sides. So that becomes just 3x on the left-hand side. 12 minus 18 is negative 6. All right. Working right along here. And then the way that we can break up this multiplication bond here is through its inverse operation. The inverse operation of multiplication is division. All right. So we can divide both sides by negative 3. Negative 3 over negative 3 is a positive 1. Positive 1 times x is just x. And then negative 6 over negative 3, negatives cancel out to be positives. 2 negatives make a positive. And so 6 divided by 3 is 2. So our solution is x equals 2. Okay? All right. Now let's take that same kind of skill and apply it to this problem right here, which we will do in the next video.